fullerenes and amorphous. These were detected out in space. Amorphous, you know, you could buy amorphous carbon boats. They're very high temperature cookware, basically. Okay, let's continue on. Not everything's a solid, you know. For example, C60, you have a bunch of these C60 molecules packed together to form a solid. And so when we're looking at C60 solid, this is the way we represent it. C60 solid means that we have all these soccer balls, you know, like, I don't know how I should write it out. And then they're just packed together, but these aren't going to be bonded like gold. You know, gold, you look at the atoms of gold, those are strongly held together by what we call metallic bonds. But these C60s are easy to break apart. These C60s are held together in the solid by something called, it's not a bond, but what it is we call it an intermolecular force. Inter means between, and molecules. Intermolecular force means these forces of attraction between molecules, and they're fairly weak, and so intermolecular force. And so not a bond, rather intermolecular force, which is fairly weak, which means it's pretty easy to break these off. In other words, it's not hard to melt this stuff or to vaporize it. All right, so some of the other elements are, you know, we have a whole series of elements. Like, for example, if we look at oxygen, interestingly enough, forms O2. This is the most stable. What's going to be rarer would be ozone. Ozone is O3. It's fairly unstable. Now, when we breathe in oxygen, you know, we're breathing in actual oxygen, what we call molecules. We don't want to be breathing in ozone molecules. And the reason these are what we call molecules is these are two or more atoms held together, you know, to form a distinct unit. And the distinct unit would be like O2 here. We have O, like this, which would be just oxygen. This is called atomic oxygen. Atomic oxygen isn't as stable as this. This is diatomic oxygen or molecular oxygen. And so it just turns out that the two oxygens like to bond to each other. And 3 don't really like to bond to each other, because if you go to 3, it becomes unstable, and 4 won't. It refuses to bond to each other. And so we have something like that. Now, these are individual molecules, so if we look at air, then air is going to have oxygen in air, but it's going to look like this. If we look at a sample of air, it's mostly empty space. And then we'll have some oxygen molecules here. And these oxygen molecules are just moving about in random directions like this. But air consists mostly of, not oxygen, air consists mostly of nitrogen. Now nitrogen does a similar thing. Diatomic nitrogen, or molecular nitrogen, is much more stable than atomic. And there's no ozone equivalent for nitrogen. And so nitrogen is like this. And so we have some nitrogen molecules, we have some oxygen molecules, and these are all just moving about. And so this is what we call a molecular substance, diatomics. There are a whole bunch of diatomics. Do you know the diatomic elements? Probably, maybe not, but let's talk about the diatomic elements, things that form, like hydrogen gas. Hydrogen gas is similar to oxygen gas in the sense that we form H2 molecules. And so if we can easily introduce hydrogen into air just by having some H2s in here. Hydrogen gas. What else? What else would be hydrogen? We go on along the periodic table. Nitrogen. What about carbon? I skipped carbon. What about boron? Those form diatomic molecules as well, but those aren't stable. And so the common ones that are stable are going to be hydrogen. Nitrogen forms N2. Oxygen forms O2. These are all molecules. After oxygen comes fluorine, which forms F2. And so these elements, these atoms like to bond to each other in this way to form a diatomic, and that's stable. But what happens when we get to neon? If we add neon to this, is neon a diatomic? No. Neon's just an atomic. Yeah. And so if we were to add some neon gas to our air, which we could easily do just by getting a neon tank and just opening it, then we'll just see atoms of neon. If you breathe in neon, do you have to worry much?
No.
No, you don't. It doesn't really react with anything. Neon's fairly stable. Like helium. If you breathe in helium, well, you got to worry about, asphyxiation. But you don't really have to worry about much else. And so this forms an atomic. Okay, so the way we represent the formulas is different. And so if it just forms a single atom like this, then we represent it just by the symbol like this. If it forms a diatomic, we represent it with the molecule. If it forms a larger one, like C60, then we represent it as C60. Some of the other common ones would be some other molecular elements. Would be sulfur. Sulfur is spelled with a U, UU. Is that right? Sulfur, yeah. UU, and the most common is yellow sulfur. Yellow sulfur is S8. And then we have white sulfur. White sulfur we just represent as S. These are both solids. Yellow sulfur forms these crown rings. It's just 8 sulfur atoms bonded in a ring structure like this. So we'll just use a line to show how they're connected. Like that. Whereas white sulfur is rubbery. And what it does is it forms something called a polymer, like this. There's no real beginning, no real end. These strings can go a long ways, and they're kind of amorphous. We can stretch a little bit, and so it's like rubbery polymeric sulfur. And so it's not atomic, it's not molecular, it's kind of a lattice, but it's what we call an amorphous lattice or classy lattice, in which, and so the easiest is just to use a single S to represent this this way. Phosphorus, we have P4, which is white phosphorus. White phosphorus is fairly unstable. In air, it'll start to glow because it burns slowly in air. We also have red phosphorus. Red phosphorus is like white sulfur. Yeah, but a lot more stable. Red phosphorus, though, they use in matches and stuff like that, so it's not totally stable. It forms an extended kind of structure like this. Not really crystalline. But, there's no real beginning or end. It's just a lattice kind of thing. It just extends. All right, so what are we looking at? We're looking at elements. So, in other words, let's summarize now. Elements can occur as atomic elements. Atomic elements would be things like helium, neon. You know any others? Argon, krypton, those are all like helium-like gases in which single atoms are in the gas phase. Then we have molecular. Molecular elements would be like sulfur, S8, but not white. White sulfur is not molecular. White sulfur is neither atomic nor molecular. What do we call it? More of a kind of a lattice, kind of an amorphous, isomorphous lattice kind of thing. Just extends out. What else? The diatomics, hydrogen. There's 7 diatomics. Hydrogen, nitrogen, oxygen.
Chlorine. It can't be that.
Well, chlorine's diatomic, you're right.
Yeah.
Oxygen, fluorine, chlorine, bromine, and iodine. That's the 7. And so we have to go. Do you see what, chlorine? I think everybody knows chlorine. What's the symbol for chlorine?
Cl.
Cl, bromine's Br, iodine is I. AT is radioactive, so we don't really worry about AT so much. So those are the 7 diatomics. And so we talked about, and then we have the lattice type elements. Lattice type elements would be like gold, which would be crystalline lattice. Silver would be a crystalline lattice. Silver forms beautiful needles. Have you seen the crystals of silver before? Maybe not. They form, well, actually they're much more complicated than simple needles. So let's just take a look at silver crystals. These are called like dendritic type patterns. They're very nice crystals of silver. Silver dendrites. From afar, these are magnified, so from afar they look like needles. This is typically what it looks like, a little forest. We have crystalline, right, lattice, and we have, what's the other type of lattice we have? If it's not crystalline, we call it amorphous or another word for glassy, right? We have amorphous or glassy. And so metals are hard to get. Let's see amorphous metals, if they've made any progress on amorphous metals. Well, it's hard to make amorphous metals because metals love to crystallize. And so most metals we just think, they call it, like, for example here, a metallic glass or glassy metal or amorphous metal. But they'll have different properties because it's like diamond versus graphite. Just the way it's put together, they have totally different properties. Like, even though they're made, graphite is 100% pure carbon, diamond is 100% pure carbon. But because of their structure, they have quite a bit different properties. All right. So normally, you want to summarize the material, but you don't want somebody else to summarize the material. Normally when you're studying, you want to summarize it in your own words. If you summarize it in your own words, you remember it a lot better than memorizing somebody else's summary. And so usually the summary part, I like to leave the students to, this is part of data reduction. This is part of the science, part of science, kind of thing, is you just figure out things. Okay, those are the elements. Let's take a look at the compound. Now compounds, these are 2 or more elements. And they're going to be attached to each other. We're going to have 2 or more elements. These are atoms. And these are going to be bonded together. with fixed composition and properties. It's like the element, you know, how can they tell, you know, how can you tell real gold from fool's gold? How can you tell real gold from fool's gold?
What?
How can you tell the difference between real gold and fool's gold?
Like a fake gold?
Yeah, fake gold. All right.
Well, are you given time or do you have to find it right then?
You're given time, as much time, and
Okay, well then, if it's fake gold, it'll react with water and like everything. And it'll get rusted.
oh, then you know, I want to sell you some gold.
Yeah.
I have some gold that it doesn't
At that
react with
point,
water.
You said time, so that's what I said. But if
Oh.
you want to find it right then,
Okay.
Isn't there like a test or something?
Yeah, I know a test. You just put it in water, and the fake gold will kind of fizz and dissolve, but the real gold doesn't. I got some real gold for you. No?
That's not, but I don't.
You scratch it against something, I believe.
Yeah, you could scratch it against something. I mean, you'd look for the color for one. You know, if I tried to sell you gold, that's the wrong color. But you could try scratch. Have you ever heard of fool's gold? That would work for fool's gold. You can scratch it because it's not very hard. It'll crumble away. It's much more brittle. There can be different properties, and so you know, when we're talking about fixed composition, the properties of gold are fixed. I mean, if you look at it, amorphous metals, the properties aren't necessarily going to be fixed. But if you look at gold, the properties are going to be fixed. And so, what are the properties of gold? We could just look it up on Wikipedia. It's pretty easy to find. Now, a lot of people don't like it, but you know, these are pretty good actually. This table of properties here are really really useful. So if you look on the sidebar here, gold, you know, one of the things, we can try to melt the stuff. Well, obviously it's solid, it's going to have certain color, but the melting point is fixed. That's because the structure of gold is fixed. The composition of gold is fixed, so the property is fixed. So the melting point is 1,947.52 degrees Fahrenheit. So almost 2,000 degrees Fahrenheit to melt it. So it's not easy to melt. You know, the bonds are pretty strong. If it's easy to melt, that means that they aren't held together strongly. You know, the bonds. To boil it's even worse. You know, you need 5,400 Fahrenheit to melt the stuff. It's going to be really hard to do. I mean, to boil it, to vaporize it. But you know, one of the quickest ways to test is by density. You know, the density of gold is the grams per cubic centimeter. You know, there's some things that are dense. Like, you know, there's the old saying, you know, what's heavier, a pound of gold or a pound of feathers? Which one's heavier? They're the same. That's supposed to be the trick question. They're the same, you know, the same weight. But what's different is the density, because, you know, a pound of feathers is like this, a pound of gold is like nothing. So gold is much more dense. You know, gold is one of the most dense elements on the periodic table. It's around 19 grams per milliliter or cubic centimeter. So it's very heavy, it's very dense stuff. So we can use these. These properties are fixed. The composition is fixed. This is pure gold. The properties are going to be fixed. Well, the compounds are the same thing, even though we have two or more. Like, for example, water. Water is what we call a molecular compound. This is a molecular compound because water occurs as water molecules, H2O molecules, two hydrogens and an oxygen bond together. And so let's take a look at the water molecule here. This is the water molecule. Hydrogens is smaller, so you can see this is called a space tilted model. The oxygen is a lot bigger than the hydrogen. The hydrogens are attached here. This forms as a distinct unit. When the hydrogens are bonded to the oxygen, what this dotted line is showing is showing the force between the molecules, which is called intermolecular forces. This is what holds the water molecules together in liquid water, are the intermolecular forces. But they aren't terribly difficult to break. All you need is 100 degrees C, and you can break the water molecules apart from each other. That is, break this intermolecular force. But if you want to break the hydrogens from the oxygen, you're going to need a heck of a lot more than that to break the hydrogens from the oxygen. So it's got a fixed composition. It occurs as discrete units. These discrete units are molecules. That's an H2O molecule. And so H2O can occur in different, what we call different phases. We have H2O solid, which we call ice, and this is given the S there. We have H2O liquid, which we call water, and we have H2O gas, which we call steam. And so it can occur in different phases. H2O liquid, the difference between solid and a liquid is a solid, these are frozen in position. In a liquid, these can move, but they're still stuck together. In the gas, these are completely separated, far apart from each other. So that's H2O. That's a molecular compound. Okay, we also have lattice type compounds as well. And so an example of that would be salt, NaCl, solid. Salt, this is a lattice style compound here. And that is, we aren't going to have an individual molecule of salt. There's no such thing as a molecule of salt. It does not form molecules. Well, it could in gaseous and rare states, but when you put salt in anything, it occurs as this. So we'll say, here's some salt crystals there. It's a solid. It occurs as a lattice like this. And so it turns out that the sodiums are here, the gray, the chloride are here. This is sodium chloride or salt. And you could have big crystals and small crystals. There's no one size crystal. And so if you want the smallest one you could have is just one sodium, one chlorine. But you can make it bigger, but it's just adding more. And so it forms a crystalline lattice. The composition is fixed. Composition is, you have to have the same ratio, a 1-to-1 ratio. One-to-one ratio, and the properties are going to be fixed. So it took almost 2,000 Fahrenheit to melt gold. How much does it take to melt salt? Time? Okay, sorry. Let's take a look at the time. What time do we go to? 12:20. That's right. On Tuesdays is a little weird. On Mondays and Wednesdays we go to 12:35. But on Tuesdays I guess we only go to 12:20. So let's stop it here.